All right, continuing to explore the force of gravity. It can be tricky, can get simple or easy. We said there's a universal force of gravity that Newton created to explain the motion of planets. If we look near the surface of Earth, we can use the mass of Earth, the radius of Earth, and we can get, hey, that turns out to be our free flight acceleration. So now near the surface of Earth, the force of gravity, the pull downward, non-contact, from Earth on any object is just mg. So that's what we'll use. Okay? We need to really distinguish mass from force, and we need to distinguish, or we need to clearly define or even talk about the word weight. It's tricky. I want to comment that we can do this on the surface of Moon or Mars, whatever. Near the surface of Moon, we find that the force of gravity is about 1/6 as much as near the surface of Earth. And so when I throw something on Moon, the acceleration in free flight on Moon will be about 1/6 of Earth's free flight acceleration, g. Okay? And why? Because, well, Moon has less mass. It does have less radius, so that'll increase the force, but it's got less mass. You can calculate it easily with these numbers. It's kind of fun. But let's go over here and just explore this real quickly and then get to that. Remember, mass plays two roles. Inertia, or resistance to acceleration, and the property of gravity, right? And those are very different things. If we have the mass of R of 1 kilogram, what is the force of gravity near the surface of Earth? Well, it's mg. G on Earth is 9.8. We can use 10 just as a rough, right? So 10 times 1 kilogram gives about 10 newtons, 9.8, right? When you're doing problems, use 9.8. Don't approximate it, but just to get a sense. So what is that on Moon? So here the force of gravity from Moon on that same object will be about 10/6 newtons, right? Close to 1.5, or 1 2/3. So we've got that. Much less. What about 10 kilograms? Well, the force of gravity, the pull downward that Earth exerts somehow without touching on that 10 kilograms is 10 times 9.8. Well, that's 98, right? Or about 10 times 10, about 100 newtons, 98 newtons. Okay. What is it on Moon? Well, it's 1/6 of that. It'd be easier to do it over here, but 100. So that's quite a bit less. So let's explore some numbers that we're maybe used to. 120 pounds. That's not a mass. Pounds is not a mass. On Earth, if you have 1 pound force of gravity, you put it on a scale, and we'll talk about scales here in a second, 1 pound, well, how many kilograms is that? Well, one thing I know is that 1 kilogram has a force of gravity, and you can check this, of about 2.2 pounds. 2.2 pounds force of gravity. 1 kilogram has a force of gravity of 2.2 pounds. That's a force. That's a mass. They're different. Throughout most of the world, people talk about kilograms as weight. That's really wrong. Kilograms is a mass. We'll talk about weight and the relationship to force of gravity in a moment. Let's say you step on a scale and it says 120 pounds. That's the amount that Earth is pulling you down, and the scale tells you how much that it has to push to balance that, so you're just standing there not falling. Well, the kind of cool thing is that on Moon, you stand on the same scale and it's 1/6 that. Wow, there's your weight loss program right there. My infomercial, you can send me $9.95 plus $20 shipping and handling. Or you're 180 pounds. You step on the same scale on Moon, and Moon pulls you down into that scale 1/6 as much, or about 30 pounds, right? So it's pretty dramatic, it's pretty cool. But there's this confusion between kilograms, it's not a weight, it's a mass. Pounds is a force of gravity, or any force, any of the forces that we've discussed. So let's explore this and show just how tricky it can be. All right, let's come over here. We've got the force of gravity is mg near the surface of something. Suppose we drop two objects here. So I'm going to take two objects, and I'm going to drop them just like Galileo. And I got to set it up right. I got to have the bottoms that are going to hit be level, and then I got to release them at the same time. So I might not get the right result first. I got to do it over and over. Let's do it in this case, lining up the bottoms. Drop them, who hits first? You really should pause and do this. Just take a couple things and do it a few times and see. Make it so that the difference in mass is so significant that no small variation really counts, right? So if they're pretty close to hitting, well, let's see. So what have I got? I've got a force of gravity here on A. And then I've got a force, this has more mass, so Earth somehow pulls stronger on B. It's got more to grab onto in a sense, right? So who's going to hit more? Well, the force of gravity is stronger. If this has twice the mass, I've got twice the pull of gravity. Right? So you're going to go, hey, Earth is pulling strong on it, it's going to hit first. But wait a minute, mass plays another role. Not only does it increase the amount Earth can pull on it, it increased the inertia. So B is getting pulled stronger, but it's resisting more. And so, for instance, let me just call that plus, and we know that we said free flight, we didn't say anything about mass with free flight. So this is free flight. If that's plus y, AY is equal to plus G for both. If that's true, they should hit at the same time. We don't need a component table. Don't do that if it's not necessary, but in a lot of cases it will. And we've got the Newton's second law. So in this case, I've got the sum of the force y equals ma times the acceleration in free flight, which is g. And the sum of the force y is equal to mb, acceleration free flight. So what's happening? Well, the acceleration, the only force here is the force of gravity on A. And the only force here is the force of gravity on B. If you have more mass, you get pulled more. That's property 1, or property 2 of mass. But if you have more mass, you resist more. Double the mass, you double the inertia, but you double the pull. The acceleration, the ratio here stays the same. And so if you drop these guys, you should be able to prove that on your paper, that no matter the mass, they'll hit at the same time with negligible air resistance. Okay, so that's one thing. All right. Mass playing two roles. It is responsible for the force of gravity, but it is also an inertia. If you push the same on a little kid and an elephant, the kid's going to accelerate more because the elephant resists more inertia. In order to get them to accelerate the same, you've got to push stronger on the elephant, weaker on the kid, and then they will accelerate together. Stronger pull on the elephant, weaker on the kid, and they will accelerate together because stronger pull, but more inertia. Weaker pull, less inertia. And the ratio is the same, and that's why it happens. Okay, let's take another look. What are we doing? How are we doing? And that's kind of a tricky one. Make sure you could prove that if you were asked that on an exam. Now, let's take another look at a situation that explores the distinction between gravity and normal. So just put something here. Now this surface could be a scale, or it could just be a surface. Here's my receiver, my object that I'm going to focus on, one that I care about, and look at the forces on it. And I've got some forces. You can see it's great. You could just look. What's touching it? Okay, the surface. Is there any friction? Well, there might be some roughness, but nothing's being pulled side to side, so there's no friction. There's only a force from the surface, the normal force, down here, but I'll draw it up here. And then, of course, the non-contact word force, not from the surface, but from every single rock and piece of water and drop of water, everything, pulling down with the force of gravity. Now, in this case, we know if static, which means v equals 0, equilibrium, which means acceleration is 0, then these forces have to balance. They don't go away. And so in this case, I don't know, I need a coordinates. I've got to choose one. Let me call that plus y. AY is equal to 0. I don't need a side to side, so why do it? I don't need components, and I can go straight on to say I've got a normal force is in the up direction. Oh, let me do this. The sum of the forces in the y is the mass of the receiver, AY. Well, it'll get interesting here in a moment. So what have I got here? I'm going to put n in as a positive because I chose up positive and it's up. I'm going to put Fg. Well, we know that. That's mg. That's the mass of what? The receiver, g, is equal to. And then I look here and I go, oh, you said it was equilibrium. Could be dynamic equilibrium, doesn't even matter. The acceleration then is 0. Be careful. These are very different forces. This is from the contact surface, and this is from the entire Earth pulling with that magical non-contact force. So now I solve. And now in this case, yes, the normal force balances mg, but they are very different forces. Put them in separately because this is the only case where this is going to work out nice and neat. Let's take a look here. I'm going to add to this real quickly. So I push down. So in this case, can you see this here? In this case, I put this on a scale and balanced it. The normal force is balancing the force of gravity. If I push down, the force of gravity didn't change. The force of gravity just stays mg. It doesn't care what you do. And I'm pushing down. So the normal force has to increase. So let me put a push down here. If I push down, force of hand, or me, or whatever, and if I'm still static equilibrium, I'm still going to go here. So now I introduced another force, and it's downward. So I'm going to put negative F hand. And now I'm going to solve for the normal force. Move this and this over. Plus F hand, which is to say that the surface has to support or balance not only the pull down of Earth, but the push down from my hand. Right? And so clearly the normal force. And if this is a scale, then the scale would read more clearly. Here, the scale would read the force of gravity, because that's what the scale balances, the force of gravity. Here, the scale would obviously read more. If your friend's, stepping on the scale and you push down on it, it's going to read more. Now what happens? Now let's go along here and flip it. All right, we flipped it. So now force hand is up. I move it to the other side, and the normal force has been reduced. So if I lift it like this, oh, lift it up. Scale doesn't have to push up as much, right? So clearly, if I push down, the scale's got to push up more. If I pull up, the scale doesn't have to, because I'm helping it balance the force of gravity. Okay? So this is an important distinction. So again, if this is a scale, the n is what the scale reads. Right? That's what the scale reads. And so we have interesting problems with elevators and other cases. So the punchline, or the thing to hold on to is, when you put in your free body diagram, n is n. If you tilt it, then it is still perpendicular and away from the surface. mg is mg. That is not the acceleration. In this case, notice the acceleration is 0. This is not the acceleration, for goodness sakes. You can just see it. It's not accelerating. That's not the acceleration. This conglomerate here is the force of gravity for reasons we explained before. All right, that's just a force. These are forces. Ma, is that a force? No. Ma is not a force. It has force units. These pushes and pulls, these interactions, cause the receiver to have that acceleration. This is not an interaction. These are from sources, from objects on a receiver. This is the mass of the receiver and the acceleration of the receiver. This, ma, is by no means a force. Okay? Just put in the forces, then solve. So set it up, then solve. Don't jump here. You're going to make a mistake. It'll get tricky. Do this. You'll always get it right, and it can be quick. Okay, so let's take the case of an elevator. How are we doing?
3 minutes.
Okay, so an elevator. Take that same situation. Let's get rid of this. Let's get rid of it right here. We know that this is mg. Let's get rid of this. Okay. Now, let's see what we've got over here. Suppose there's multiple cases. So how about we make a table and we have velocity and acceleration. So suppose the velocity is upward. Could the acceleration be 0? Sure, that means that you're not changing velocity. Could the acceleration be positive, where I'm calling positive up? Sure, you'd be increasing speed, which is what happens when the elevator starts. Could the acceleration be negative, where I'm calling negative down? Sure, you'd be decreasing speed. Right? All those could happen when you're moving up. First you increase speed, then you coast along, and then you decrease speed, stop, and the doors open in your elevator. So how do you analyze that? What would be true of the normal force? If I come down here, this is still my free body diagram. If the acceleration is 0, these have to balance. It doesn't mean I'm not moving. This would be dynamic equilibrium. In that case, these do balance. You're still moving up. And in that case, we do have an acceleration of 0. And in that case, the normal force is equal to mg. And your scale would still work. Now, if you accelerate up, the only way that's going to happen is if the force up is greater. In that case, you've got an ma over here. The force n is greater, so the acceleration is up. What if the acceleration is down? If this is negative, if that's negative, then n is less. As the elevator slows down, you feel like you're floating. You feel less of the ground. So in this case,